Welcome back to Next Up, where we have a closer look at one specific question, inform us a little about the background, and then make an informed decision on how to answer the question, specifically in coding and interview environments. And we are still looking at a lot of questions from machine learning and deep learning. Today, the question would be about why is ReLU, rectified linear unit, better and more often used than Sigmoid in neural networks. And before we make our decision, let's take a deep dive into different activation functions and find a little bit more about their pros and cons. And today's deep dive website comes from medium.com, Theory of Everything, Avinash Sharma, Understanding Activation Functions in Neural Networks. So what does an artificial neuron do? Simply put, it calculates the weighted sum of its input, adds bias, and then decides whether it should be fired or not. So consider a neuron weight times input summed upon then plus bias. So we need, like generally speaking, we need the activation function. Otherwise, all those different neurons with their like linear weighting and adding will just collapse into one big linear function, or like one big matrix, so to say. And those activation functions basically take the linearity out of it. So that's the short answer why we need them. But let's have a look at different activation functions. Looks like the simplest one here is the step function, which is basically just an if-else function. If greater than threshold 1, otherwise 0. And then here the threshold is basically if x is greater than 0, then it's 1. Otherwise, it is 0. So it's a step function. And it's kind of like a binary classifier is what they're also writing here. And you want to use it if you want to use only activate one neuron, another should be 0. A different one is a linear function. It's a straight line function, which would not necessarily help too much. So if it's so linear, it will just like multiply one scalar value to what you have already. But now we actually get to the interesting part, and actually that comes close to our question, why ReLU over Sigmoid? So Sigmoid here defined as 1 over 1 plus exponent function e to the power of minus x. Looks like this, called Sigmoid, because it kind of looks like this S shape here that kind of asymptotically moves towards 1 and asymptotically moves towards 0 for x going to plus infinity and minus infinity. And we have like this thing as 0, we have exactly 0.5. So that's basically just how Sigmoid looks like. So let's talk a bit about advantages here. Unlike the linear function, the activation function is always going to be in the range 0, 1, right? Because it's capped there, and it's kind of like asymptotically goes to 0 and asymptotically goes to 1. So how about the disadvantage? Towards the end of the sigmoid function, the y values tend to be less varying, right? They only just like fizzle around 0 and fizzle around 1. So in practical terms, if we have like a gradient going on around those values, this gradient is just vanishing because nothing's happening much, because the sigmoid function just like smoothes it down to the same value. It's like they say it calls like a near horizontal curve. And what a vanishing gradient means for a neural network is that we can't learn much from it. We don't know how much error we have received from comparing our output with the desired output and back propagate that error via the gradient. At this point with the sigmoid function, the gradient will just vanish, go away. Okay, next up is the tan-h function, which looks pretty similar to sigmoid and has a specification looks like this: 2 over 1 plus e to the power of minus 2x. So it's basically, you have like 2 in the numerator, and then you have -2 in the exponent is the one minor difference, and then you have like -1. So kind of now this time we basically have a range from +1 to -1 with still this asymptotic behavior around plus infinity and minus infinity. And exactly as we're seeing it here, so it's like a scaling factor, 2 times the original sigmoid, -1. So we scale it now and have like a range from +1 to -1. And x is also scaled times 2. Same problems will arrive. It's still nonlinear. But again, vanishing gradients will be a problem here too. Now to the star of the show, ReLU. Basically is maximum of 0 and x. So we keep the original input x when it's greater than 0, and we threshold it up to 0 if the input value is smaller than 0. So that means we kind of just, only treat the input further if it's a positive input, and if the input is negative, we just like leave it where it is. And so since it's linear, it still has like a gradient here. Plus that gradient is also like not vanishing. That's great. It still goes to infinity as our values go to infinity, so that's an issue. But the very good thing is like it has this sparsity component to it, right? So like everything smaller than 0 gets just erased further down the pipeline. It's just like stays 0. There's no discrimination on any negative values anymore. So like any negative input will just be indiscriminately be handled as 0. So in other words, all activations will be processed to describe the output of the network. Activation is dense, it's costly in terms of tonnage or sigmoid. But if we do ReLU, we only have like these positive values that get processed further. So if our input data are basically normally distributed, we would have only 50% of the data actually going forward, and the rest will be just like set down to 0. The authors here come to their own conclusion, right, and probably will have a tendency to use ReLU over other functions here. ReLU works most of the time as a general approximator. So that's that. But in more concise terms, actually a nice answer came from stackexchange.com on that very same question. What are the advantages of ReLU over Sigmoid in deep neural networks? Exactly what we just discussed. Very concisely described here in a nice way that you could actually also tell during an interview. The 2 additional major benefits of ReLU is sparsity and reduced likelihood of the vanishing gradient. Recall again that ReLU is max of 0a, where a is the output of your linear weighting and bias. The major benefit is the reduced likelihood of the gradient to vanish. That arises when a is greater than 0. Then the gradient has a constant value. In contrast, the gradient of sigmoid becomes increasingly small. You remember, as we asymptotically go to 1 or 0, there's nothing much going on anymore. It's just like a 0 gradient there anymore. The constant gradient of ReLUs results in a fast way of learning. The other benefit is sparsity. Sparsity arises when a is smaller or equal to 0. The more such units exist in a layer, the more sparse the resulting representation. Sigmoids, on the other hand, are always likely to generate some non-zero value. I think the authors in the other website briefly touched on it and said like it will always be like a dense output. So we will have like a dense representation. Sparse representations seem to be more beneficial than dense representations in order to train our network and learn the underlying aspects of the problem that the network tries to tackle.